The reason this, it sounds like, from what you're saying, it sounds like you're thinking correctly, but let's see. So, energy required, right?
Right.
Right.
Well, you got you need 2.4 joules for every gram and every degree Celsius, right?
Every degree.
I thought it was every degree Kelvin.
Well, Celsius degrees and Kelvin degrees are the same size, right?
19, 20 joules.
And you're talking about a change in the temperature, so a change in Celsius is exactly the same change as that change in Kelvin.
They just differ by a constant.
Now, the Celsius temperature is different than the Kelvin temperature, but they differ by constant, by 273 degrees, okay? So, if you go from this temperature Celsius to this temperature Celsius, you're going from the same temperature Kelvin to the same temperature Kelvin,
Right, okay, yeah.
but the Kelvin temperatures are both 273 higher.
Right.
It's just like in calculus, if you do a definite integral, it doesn't matter if your antiderivative includes a constant or not, it subtracts off.
Right, okay.
Okay?
I see.
So, yeah, that's one, thing that we can easily dispose of, okay? So, Kelvin degrees, Celsius degrees, same size, so it doesn't matter if this is per gram Kelvin or gram Celsius, it's equivalent, okay? Because we're talking about, again, a change in temperature, not an absolute temperature or a temperature on the scale, right?
Right.
Okay? So, we have that. And so what do you need to know? You know how many grams and how many Celsius degrees, right?
Mm-hmm.
So you need to know okay? Well, how many grams you got?
80.
You got 80 grams. Because you have 100 milliliters, right? And a milliliter is just a liquid cubic centimeter, okay? And you got 0.8 grams per cubic centimeter. Now I said 8/10 the density of water. Presumably you know the density of water to be 1 gram per cubic centimeter. Now that's at a certain temperature because the density of water changes with temperature. Not insignificantly, okay? So, and so does the density of alcohol. We're ignoring the little changes. They're not insignificant in many applications, but they aren't huge either, at least within, temperatures that we normally experience. Okay, so anyhow, so you got 80 grams. Now formally that would be 0.8 times 1 gram per cubic centimeter times 100 cubic centimeters, right? And you've got from 20 to 30 Celsius degree. Celsius, 10 Kelvin, same thing.
Is there a symbol they use for the specific heat of a substance?
Yeah, you're going to get that in the last question in this whole series.
Oh, my bad.
I don't want to start with a formula.
My bad.
I want to start with an idea that you grasped just fine when I said this. A little confusion about Celsius and Kelvin degrees maybe, but you were, what I heard you talking about was exactly the right thing. Okay? So I think you understand every bit of this without a silly formula.
Right.
If you start with the silly formula, you start using it without understanding it. And eventually, maybe if you think right, you get the understanding. But if you just treat the formula as something to use to get the answer, you might never understand what it means.
True.
Right? You might never make sense of it. So we start by making sense of it, and then we develop the formula. And then you have a complete understanding. Because the last thing I ask you to do is do this symbolically.
Right.
And then I give you some symbols. Okay? And rely on you to figure out the formula.
Right.
So next time you see the formula, say, okay, I know what that means. Right? Okay, so you got this. You got your temperature change, you got your number of grams, right?
Right.
So I can reason this out in a couple of ways, and I'm going to do it because, just in such a way as to understand. At 2.4 joules per gram Kelvin, you multiply this by this, get 192 joules if I did it right. Check my arithmetic. So you could say, well, that's going to require 192 joules per every Kelvin degree, right?
What did you say?
So then delta T 10 Kelvin requires 10 Kelvin times 192 joules per Kelvin equals 1920 joules. And there you've got it. Now, this is a preliminary question. This is not the question posed in the problem.
Right.
The question posed in the problem says, okay, you got water at 80, 100 milliliters of water at 80 Celsius, and 100 milliliters of alcohol at 20 Celsius. You're going to mix them just like we did the Dr. Pepper and the hot and cold water. This is just like what we did.
Right.
This is motivated by what we did in lab. But now you're putting alcohol into the water instead of water into the water, right? And we're accounting for the different behavior of alcohol and different density of alcohol. Okay? So now how are you going to get it if you've got 100 milliliters of water at 100 or at 80 Celsius and the 100 milliliters of alcohol? This is just how you would calculate the temperature change or the energy required to increase the temperature of the alcohol, right?
Right.
So how do we go from there?